This is 4.3.2 Radioactive Decay, Applications of Separable Equations. So let's just look at the model for radioactive decay. This problem behaves opposite to a population growth. And consider a sample of materials that contains the mass empty at the time t that has been decayed into another isotope with proportionally constant. So then the differential equations represent this problem is dm dt equal to minus km. So the k here is referred to the decaying constant. The m here is the mass of the material at time t. And the t here is referred to the time. Let's just look at the half-life. So the half-life of a radioactive substance is the time required for 1/2 of the atoms in an initial amount m0 to degrade. So it means that your mt is equal to 1/2 of the m0. The longer the half-life of a substance, the more stable it is. So let's just look at the example 1. A radioactive substance disintegrates at a rate proportional to the amount present. 100 mg of this material reduced to 40 mg in 3 weeks. Find an expression of the amount present at any time t. What is its half-life? Okay, so first of all, let's just gather the information from the example 1. So what we have here is we have 100 milligram. The 100 milligram is the initial mass. So it means that you have the M0 that is equal to 100 milligram. And it's reduced to 40 milligram in 3 weeks. So it means that your time is actually 3. So this is referred to your M3. Okay, the M3 is actually 40 milligram. Now let's just look at the questions. So the questions ask us to find the expressions of the amount present at any time. It's basically asks us to find the mathematical equations for this amount of radioactive substance at any time t. And for the question B, it asks us to figure out the half-life. It actually asks us to figure out the time. Okay, so the time is actually a question mark. So when will be the mass become half? Okay, so the mass at the time t will be half of the initial. So your initial is actually 100 gram. So just substitute here. So you have 1/2 multiplied with 100 grams. So this actually give you 50 milligram. So once we have gathered the information for the example 1, let's just begin to solve this example 1 by using the differential equations. Okay, so we were going to begin by using the technique of separable equations. We're going to separate it because we have to let the m together with the tm, so you have to bring it to the left hand side. So if you bring to the left hand side, you will have 1/m together with the dm. Okay, and you have to bring the dt to the right hand side, just that is together with the k. Okay, so then you will have the right hand side, you will have minus k d. Okay, so now okay, so this for the left hand side and this for the right hand side. Okay, now let's just integrate both sided. Let's just integrate both sided. So we integrate this one and integrate this one. Okay, so if we integrate the left hand side, so you have ln m. For the right hand side, if you integrate, you have minus kt plus c. Now go to exponent both sided. Okay, if you exponent the left hand side, okay, so you have the m only. So if you exponent the right hand side, you have minus exponent to the power of k minus kt plus c. So where the e to the power of kt plus c, you can split into 2. So you can have e to the power of negative kt multiplied with the e to the power of c. And e to the power of c actually is a constant, so you can change it into another constant. Let's say a, so we have a multiplied with e to the power of negative kt. So let's just name it as the equation number 1. So means that you have two parameters that you have to figure out. That is the parameter a and the parameter k. So how to figure out the parameter a and k? So that is through the information. So let's look at the first information that we have here. So you have m0 equal to 100. So you're going to substitute your m0 equal to 100 milligram into your equation number 1. So this means what? This means that your value of m is actually 100. Okay, so we're going to substitute into here. Okay, into here. So means that your m is 100. Okay, and it's equal to your a. So your a, okay, exponent, okay, minus k. The time here is actually 0. Okay, so the time here is actually 0. So using the calculus. Okay. Okay, so you simplify it. If you simplify this one, so you will manage to get your a is actually 100. Okay, so once you know your value of a, so you're going to substitute your value of a, that is 100, into your equation number 1. So if you substitute into your equation number 1, so it means that you will have m equals to 100 multiplied with e to the power of kt. So let's just name it as equation number 2. So since we have known the parameter a, so we no longer need the equation number 1. Okay, so we just directly focus on the equation number 2. So the next task is you have to figure out the parameter value k. Okay, so you have to figure out the value of the parameter k. So how to figure out? So we're going to use the second information. So we're going to substitute your m3 equal to 40 into your equation 2. So now let's just substitute into equation 2. So it means that your m here is 40. So we have 40. Okay, equal to 100. The e to the power of negative k. Okay, the t here, your time here is actually 3. Okay, so let me highlight it. Okay, so you have the m, okay, is 40. So you substitute here. Okay, and then you have the time, it's actually 3. So we're going to substitute here. Okay, so then simplify it. Okay, so you have to bring the 100 to the left hand side. So we will have 40 divided by 100. So that is will give you 2 over 5. Okay, 40 divided by 100 will give you 2 over 5. And then for the right hand side, if you simplify, you have my exponent to the power of negative 3k. So now we're going to ln both sided. So let's just ln it. Okay, so we have ln 2 over 5. And for the right hand side, you have minus 3k on. Okay, so bring the minus 3k to the left hand side, you will become dy. So you will have ln 2 over 5 divided by negative 3. So you will get your value of k. So your value of k is actually 0.3054. Now substitute your value of k, that is 0.3054. Okay, into your equation number 2. Okay, so into your equation number 2. So then your m is equal to 100 e to the negative 0.3054 t. Okay, do not forget to write the negative. Okay, this is regards the radioactive decay, so we must have the negative at the mathematical equations. Okay, so once we obtain this answer, let's say this is the equation number 3. So this is actually the answer for the question A. Okay, the question A. Okay, so we have managed to answer the question A. This is the mathematical equations for this amount of radioactive substance at any time t. Now we're going to look for the answer for the question B. So We are interested to know what is the half-life. Okay, so how to find out the half-life? So what you have to do is you have to substitute. Okay, you have to substitute the mt equal to 50 milligram. Okay, so you have to substitute your mt equal to 50, okay, into your equation 3. So if you substitute into your equation 3, so your m here is actually 50, okay, equals to the 100 to the power multiplied with the e to the power of negative 3, negative 0.3054 t. Okay, and then you bring the 100 to the left hand side, you will have 1 over 2. Okay, and then you have the exponent. Okay, and ln both sided. Okay, so we have ln the left hand side and you ln the right hand side. This is what you will get. Okay, and bring this one to the left hand side. You will have ln 1 over 2 divided by negative 0.3054, and then we have the value of t. So the value of t is 2.296. Sorry, that is 2.2696. Okay, so this is the answer for the question B. Okay, let's just look at the example 2. So carbon-14 or C14 decomposes at the rate proportional to the mass present. So if the half-life of this C14 is 5,568 years, shows that the equations of mass at any time is this one. So then hence find the percentage mass of the C14 after 10,000 years. Okay, first of all, let's just extract the information from this example 2. Okay, and the first thing that you have to do is you have to identify the initial mass. But unfortunately, we cannot find any information regards the initial mass. Okay, so it means that you have to let the m0, okay, m0 equal to m naught. Okay, so the m naught is some constant because we do not have the information regards the initial mass, so we let it equal to constant. Let's say m naught. Okay. And then let's just look at here. So you have the half-life of this C14 is 5,568. It means that actually your T is actually 5,568. Okay, so that is your mass at the time of 5,568 is equal to the half of the initial mass. Your initial mass is m naught. So then we have the next line. Now let's just look at the questions. Okay, the question asks us to show the show these equations, and then you have to figure out the percentage of the mass after 10,000 years. It means that your t is actually equal to 10,000. Okay, and the mass, what is the mass at the time equal to 10,000? So that is in terms of percentage. So that is what we should figure out later. Now once you have gathered the information from the example number 2, let's just begin to solve this example. Okay, so we begin by these differential equations. Okay, bring this m to the left hand side. So we have 1 over m. So we have 1 over m together with the dm. Okay, and bring the dt to the right hand side, so you will have the negative k with the dt. Okay, and then integrate both sided, so integrate both sided. So if you integrate the left hand side, this is actually give you the ln m. So for the right hand side, if you integrate, it give you negative k t plus c. Okay, and then exponent both sided, so if you exponent the left hand side, it will give you m only. And if you exponent the right hand side, this is what you get. You will have e to the power of negative k t plus c. Okay, so now the exponent there, okay, we have to split into two exponents. So you have exponent to the power of negative kt multiply with the exponent to the power of c. And e to the power of c is actually a constant, so you can replace it, let's say, with a constant A. So now we have the first equations. Okay, so the next task is you have to figure out what is the parameter value for A and what is the parameter for K. So in order to find the value of parameter A and K, so you need to use the information that we have here. So let's just begin to use the information that we have here. So we need to do the substitutions. So let's just do the substitutions. So substitute your M0 equals to M naught into your equation number 1. So it means that now your M is M naught. So for the left hand side, you have M naught. Okay, equals to A. Okay, E to the power of negative. Okay, the K multiplied with the time. Okay, the time here is actually 0. So you multiply with the 0. Okay, so we simplify this one. So we have that your A is actually M naught. Okay, so substitute your A equals to M naught into your equation number 1. So if we substitute into number 1, so we have M equals to M naught. Okay, we're going to substitute. Here is the A with M naught. Okay, equal to M naught E to the power of negative KT. So we name it as number 2. So now we use the second information that we have here. So in order to find the value of K, so we're going to substitute your M 5568 equals to 1 over 2 M naught into your number 2. Okay, so you will have that the left hand side is actually 1 over 2 M naught equals to M naught e to the power of negative K multiplied with the time. The time here is 5568. Okay, so basically you can simplify this, okay, because the left hand side and right hand side both of them are having the M naught, so you can cancel the M naught here. So let's just simplify it. So we have the next line, we have 1 over 2, and for the right hand side you have e to the power of negative 5568k, and learn both sided. Okay, if you have learned both sided, so this is what we have. Okay, for the right hand side, if you learn it, you learn with the exponent, you will have negative 5568k. Okay, now you have to bring the negative 5568 to the left hand side, so we will have ln 1 over 2 divided by negative 5568. So this is basically give you the value of K. So your value of K is actually equals to 0.00012. Okay, now substitute this value into the equations. We're going to substitute your K equal to 0.00012 into your equation number 2. Okay, so then we have M equals to M naught e to the power of negative K. So your K here is 0.00012. Okay, together with the time here. The time here is T. Let me erase it. Okay. The time here. Okay. Please make sure that you do not forget to write the negative. Okay. We are talking about the model of the radioactive decay. So this is the mathematical equations for these questions. Okay. So you must have the negative because we are talking about radioactive decay. Okay. So now, okay, so we have settled with the first part. With the first part, that is they ask us to show that your M, okay, at any time, the mass at any time is actually equal to this one. So we have managed to show that. So this is shown. Okay, so let's just look at the second part. Okay, the second part is asks us to figure out the percentage of the mass, after 10,000 years. Okay, so the way to solve is actually very simple. So you have to do the substitutions again. So you have to substitute m 10,000 into, okay, let's say into your equations. This is equation number 3. Okay, so into number 3. Oh, let me put a question mark here. So you have a question mark here. Okay, into your number 3. Okay, so let's substitute. Okay, so we have m. Okay, that is equals to m naught okay, e negative 0.00012. Okay, multiply with the time. The time here is actually 10,000. Okay, let's simplify it. So you have negative 1.2. Okay, and then we will have this is actually equal to 0.30119 m. Okay, use your calculator to get the answer for the e to the power of negative 1.2. This is what you have. Okay, so okay, this is in terms of decimal. Okay, the answer in terms of percentage. Okay, so you have to multiply that one, okay, the decimal with the percentage. Okay, so you have to multiply with 100%. To multiply with 100%. So this is basically give you 30.119%. Okay, so it means that the percentage mass of carbon 14 after 10,000 years is actually 30.119%. The percentage mass of C14 after 10,000 years is 30.119%. Okay, so this is the answer for the example number 2.